Thanks for coming to the advanced track. So first of all, I'm probably going to say that a couple more times. This thing works best when I'm not just lecturing, but if we're having a preferably heated discussion. So I'm going to try to say a few things. No, I'm not going to try. I'm going to say a few things that are a little bit controversial. So why is it me up here, maybe? Why do I talk about teaching? So I taught my first sort of semi-official computer science class, a high school level AP computer science class in 1987. And I've been sort of teaching people, or trying to teach people anyway, ever since. So I taught for a number of years at the University of Tübingen, both computer science majors and minors, and also some humanities majors. And since about 2012, I've been doing a lot of professional training on programming and software architecture. And so I have I'm going to speak to sort of two experiences here, and one is to teach absolute beginners in programming, and then to teach people who are already professional programmers. And there's a bunch of shades in between that I don't have so much experience with. So at any given time in this talk, please jump in, right? And, perfectly fine to say, you're full of shit, Mike. I did this and it worked, and you're saying it can't work, or the other way around. Professionally, this is in the context of, so when I teach professionally, I do that for Active Group. We do software project development using functional languages exclusively, not just Haskell. Okay, nobody's booing, that's good. And we're also teaching, and I teach a lot of professional courses on functional software architecture, on domain-specific languages. And this fall, we'll start teaching formal methods. And we'll also run a blog on functional programming in general, which recently we've made an English language version of, even though the domain name is still in German. And we run the Bob conference, which some of you have been at. I recognize Greg, for example, who's given a great talk there. Sometime in March next year. And if you like this event, chances are pretty good. I think that you'll like Bob as well, which is not just dedicated to Haskell, but to all things that are very good in programming. But of course, a lot of the things that are very good in programming are functional programming. Let's not kid ourselves. And I'm also one of the hosts of the Haskell Interlude, if you don't know about this. So it's a weekly, no, it's not a weekly podcast, but we try to come out with a new episode every 2 or 3 weeks, hosted on the website of the Haskell Foundation. And so if you think you'd like to be on the show, so we usually have guests on the show. And if you'd like to be on it, or if you have suggestions on who we should have on the podcast, then please come to me, or talk to Farhad also, who's also one of their co-hosts. So who here likes Haskell? Okay, good. So therefore, it must be, when you're teaching somebody who's new to programming or is new to functional programming, Haskell's got to be the way to do it, right? You're already sensing that I'm probably going to say, no, it isn't. I think yesterday was there, if anybody was there at the beginner track, Farhad said, well, Mike and I, we're both sort of raised in the tradition of this book here. Does anybody know this book here? Or, okay, a lot of people, right? Also known as the Purple Book or the Wizard Book, came out in the mid-1980s, and it's one of the great books in computer science, right? Do we agree? Right, one of the top 10 books in computer science, beautifully written, wonderful examples on abstraction. There's a lot of functional programming in there. It uses not Haskell, but another wonderful functional language called Scheme. And one of the things about Scheme is Scheme is a very small language, and it has very little in the way of syntax, much less than Haskell. So if you look at this book, or I think a lot of us that like this book kind of look at it and think, oh, one of the great things about this book is that it really spends very little time explaining the details of the language, where the semicolons go, how the offside rule works, how the dollar operator differs from making parentheses and things like that, right? It's all the language is very uniform and small, and therefore we don't need to spend a lot of time in the classroom to talk about the details of the language. Instead, we can just do cool stuff, right? And so because it'd be interesting to kind of do a survey on who's read that at what stage in your career. So I read this book when I already knew programming, and I was like instantly in love, right? And this book, not only is it one of the great books in computer science, it was written, at least ostensibly, for the introductory course in programming at MIT back in the 80s, the pantheon of computer science, I guess you could say, even more so than maybe it is now. I don't know if it's still the pantheon now, but... and so, of course, right, the geniuses in computer science have written this great book. It's written for their introductory class. This has got to be the way to teach the introductory class, right? What could possibly go wrong with this, right? And now you'll notice, if you look around, if you ask people teaching at universities, you will not find so many courses teaching using that book anymore, not even MIT, right? They don't use this anymore. Why is that? Well, what happened was, because a lot of people sort of felt and thought the way that I did in the 1980s, a lot of universities adopted this book for the introductory course, not just in the US. I personally know a couple of universities in Germany. I also started teaching at the university level using this book. But a funny thing happened is whenever crunch time came, the exams, or when we look at the exercises, the solutions of the exercises that the students handed in, they weren't terrible, but they weren't as good as we had hoped, right? And so I'm going to summarize this with saying the book did not work as well as it did, as it should have, or as we thought it might, right? And I think a lot of educators, a lot of universities came to that realization, and they came to different explanations of why that is. Some said, well, it's of course because it's that tiny niche language scheme that's being used. I think the MIT people subsequently put out a JavaScript version to make it more popular, and I think nowadays they're teaching using Python, even more popular, with robots, no less. Things like that. But ultimately, a lot of educators found out that the book doesn't work, right? So it's a great book in computer science, but unfortunately, the one purpose that it was written for, the introductory course, it doesn't work for that, right? Yeah, there, finally. Yeah, good question. So a lot of people at the university that were not MIT sort of rationalize it and saying, well, we don't have the genius students that MIT has, right? So it's written by geniuses for geniuses, right? If you talk to the TAs for this class at MIT, they will tell you that it never worked at MIT either. So this works nowhere, unfortunately. So it's a great book when you already know how to program, then it gets you further. But if you're an absolute beginner, it just does not work. So don't do this, right? Even though in some circles, even on the Haskell podcast, I hear a lot of people saying that their sort of introduction to programming or to functional programming was via this book, but we're definitely not talking about the average programmer, and we're also not even talking about the average genius programmer here, right? So there's this, and this is a very common fallacy, right? Is that as educators, especially as the educators who are in this room, we love certain things in computer science, and so we think these are the things that we must teach, and that just doesn't hold up. And it holds in a lot of communities, so I'm always kind of amazed. So a couple of years back, I had the opportunity to write this paper on the evolution of Emacs Lisp, and that gave me an opportunity to revisit the Emacs Lisp manual, and it is intended for absolute beginners who've never programmed before. Good luck with that. So try that. So, and some people thought, well, the reason why this doesn't work is, well, of course, scheme is the problem. It should really be Haskell, literally. I mean, I think it was in Haskell. So Phil Wadler wrote this paper in 87. I mean, to be honest, I think he suggested not using Haskell, but Miranda, the immediate predecessor of Haskell, but he might as well have put Haskell in there. And he said, well, all those problems in the purple book and the wizard book, they are because your language, the language that they're using, doesn't have these things here. It doesn't have pattern matching, it doesn't have a syntax close to traditional mathematical notation, it doesn't have types, of course. That has to be and it doesn't have lazy evaluation, and therefore something equational reasoning. And if you had all of those things, then your course would be much better. No. So it doesn't work like that, right? So that's, here's another fallacy, right? If you teach a university class and you have sufficiently many students, Of course, you're in love with your technology, your Haskell, your scheme. I really was in love with scheme, I should say, right? What inevitably happens is that some students will come to you and they will say, well, you know, what you're doing, that is so wonderful, right? The lambda calculus, you know, I'm so in love with the lambda calculus. With Haskell, pretty much, after a while you find out two things. First of all, it doesn't really matter what you teach, right? Some students, there's always some students that will come up and they kind of look like this, right? So it's very easy to convince yourself that you're doing well, at least in a university classroom setting, that you're doing well, that your teaching is getting there, it's connecting emotionally with the students. But again, when the crunch time comes, when you're doing exams or you're looking at the exercises that students are doing, it is not so great. Or at least that's what happened to us very consistently over many years. So that's kind of the starting point, what I'm going to try to say today, right? Is that what constitutes sort of effective teaching is not the things that maybe immediately come to your mind, right? And I think they're still going to be sufficiently close to what you want to do anyway, but there's a couple of things that you have to take into account. Obviously, I mean, here's a book I recommend called Why Don't Students Like School by Daniel Willingham. And it has these sort of marquee, like banner, you know, proverbs, if you will, as chapter headings. Here's one chapter heading from that we all know as, I think, there's a question, I'm sorry. Yeah. So I'll try to summarize, right? So you were referring to the last point here, not to the last point, the static type discipline here, the static type discipline point. And you asked the question whether static types don't make it easier for learners, right? Is that a fair summary, right? I mean, we'll get to that point eventually. So one of the things that you need to cater to is when you teach, you tend to write correct programs, right? But of course, your students, they will maybe make mistakes. And then they will make mistakes when you're not there to help them fix them. So then the question is, you know, how do you do good feedback so that students are able to fix their mistake even when the teacher is not in the room? And maybe static types would do that. So it's conceivable that they might do that. On the other hand, read GHC type error messages. Right? And I know some very famous Haskell-oriented educators just tell students to ignore the error message and just look at the line number. I'm not going to name names here. And that should be a little red flag. That so you're not wrong, is what I'm saying. So your idea is right, that you need to provide good feedback, but maybe types are not the best way to do that, so far as we know. Yeah. Yeah. or get hot, as Simon Payne-Jones would like to say about Haskell programs, right? Yeah. Very good point, right? What is our goal here, right? And so what I'm going to get at is I want to enable students to, on their own, write programs that solve problems that are interesting to them and that are amenable to a solution by computer. Is that narrow enough?
I don't know, because
Okay, amenable to students, it's two problems that I consider relevant. There's some room here. I mean, of course, this is not like you go in a straight line from your requirements to what you do. I mean, one of the things in teaching is some of the things you'd like to teach, I don't know how to do them, so I don't teach them, right? So, yeah.
fiddle around.
Yeah.
On the other end, you have respect. Where on this
So question is, on what spectrum between formal specifications and formally proven correct programs, and I'm going to do trial and error to just hack together something, I think that's a more involved question than you realize, or than, so I'm going to stick to my, so first, so maybe the starting point is, I don't care how it's done, right? So I'm, at this point in the talk at least, formal specifications, theorem prover, doing things by trial and error would all be possible means to arrive at that result. So I'm not asking so there's two questions, sort of what kind of technology or approach, methodological approach do I consider relevant, but there's also this question, what works in a teaching context, right? And I think we agree that we don't really know how to go all the way to formally proven correct programs in the first semester. Maybe that's one starting point. Maybe we do for very small programs, right? So not the programs that I think I want to write, right, anyway. And, but one of the questions we can ask is trial and error an appropriate methodology to teach, right? And I'm going to say that it's not, right? And so if that worked, all kinds of things would be very different, but my very consistent experience has been that it does not, right? And that there's numerous other problems that come with it, and so I'll get to that, if that's okay. Yeah, but this is the kind of discussion. Now we're getting into it, so you all listen to people raising their hand and try to do the same, okay? So, and we'll get to we'll return to the types question of course, later, and we'll also return to the trial and error question later. So here's a couple of common fallacies, right? A common fallacy, sometimes known as, forget what it's called, the teacher's curse or something like that, right? Is you know something, right? You already know the material that you're going to teach and your students don't. So there's a difference between you and your students, very difficult to put yourself in your students' shoes, if you will. And therefore, what seems compelling to you, the way that you explain it, the material that you're explaining, does not necessarily translate into a good learning experience for your students. And that is, I find it very difficult to work around this one, but you should keep it in mind, right? So, and if possible, measure in some sense how well you're doing. Maybe here's a very spectacular failure in this space. I don't know if anybody's heard of the one laptop per child project, and that now is going to get to your, issue right there. Right, so one laptop per child, the idea, I'm going to oversimplify a little bit, but the idea was to put a very simple computer into the hands of a lot of people, specifically in developing countries. And it was built on this idea called constructionism that you find here. And so the idea was that, especially if you give children access to tools and materials about stuff that is interesting to learn, they will just teach themselves. So specifically Seymour Papert, also notably at MIT, really hated the classic classroom where somebody's in front and tells students something. And so the one laptop per child project really, if you don't remember it, that's because it was a failure. In many ways, the hardware I think didn't work as well as it should have, but I'll get to that next. But one of the problems was that approach to learning or to teaching or imparting knowledge just did not work, right? And but it sounds so nice, right? It really sounds, everybody, you're empowering people. Everybody can learn on their individual learning path. It sounds very pleasant, right? Yeah.
Yeah. So I think there may be a bit of a bias here. In the sense that,
no shit.
Well, I can mostly speak about myself and people I know, that a lot of us are essentially self-taught.
Yeah.
Even those that have gone through formal education, as far as computer programming goes, we're mostly self-taught. And I think a large bias is that we assume that everyone else is just like us in that way.
Yes, exactly.
So what happened to me was my neighbor gave me a computer and a book on Turbo Pascal, and I started I just got cracking and I learned programming by myself, and that makes it easy to assume that it would be the same for everyone else. But most people are not like that in my experience.
Yes, exactly.
And a lot of them still need to learn programming, and
Yeah. I mean, specifically, one of the things when we looked more closely in my university days at how, so I'm sorry, I should probably summarize briefly, right? A lot of us here, okay. I was in Japan last week. I'm jet lagged. So I remember I remember the excuse from this morning. So I remember one of the things when we started evaluating university classes, we found like a particular kind of a university class that I'll get back to later. What happened is there were two groups of students, right? There was all kinds of teaching going on, people, teacher, professor in front, showing stuff, writing things on the blackboard and so on. But ultimately, when you checked out what the students were doing, right, there was one group that succeeded, and if you looked at how they had succeeded, they had essentially taught themselves. So the class mainly told them what is relevant, but didn't really teach, right? And then there were the failures, and there was nothing in between. Right? And so, so very well taken, that point, right? There's another dimension to this. I think that's especially poignant given the fact that one laptop per child was designed for children in developing countries. And it's this one. So here's a great article by Alan Kay on the early history of Smalltalk. So Alan Kay famously coined the phrase object-oriented and worked on the Smalltalk project. And early on in the Smalltalk project, they thought that, the Smalltalk people, they think that Smalltalk is the greatest thing. It's hard to imagine, here at ZuriHac, right? They think Smalltalk is like the greatest thing. So therefore, it's got to be like the greatest thing for children, right? And so they started, bringing children in and teaching them Smalltalk. And a couple of the children were like, "This is so great. This is so wonderful. Thank you for teaching." Right? And after a little while, I don't know if it's on here, after a little while I found out that across the sort of breadth of students, it didn't work particularly well at all, right? And so there were a couple of students for whom that approach worked, and they probably would have thrived in any environment, but maybe 80, I think somewhere in the paper it says 80% of the students didn't take to that approach well at all. Right? So they fell into that same trap, even though Smalltalk is so wonderful and it's so intuitive and they have that graphical environment, much better than GHC, compile. Yeah.
But 80% of students of what kind?
Of what kind? Yes.
Of those who wanted to learn programming, of those who wanted to learn that particular kind of programming, just of random students in the school?
No, they were not random at all. I think those were students that were interested in programming, first of all, so this was not a mandatory high school class. But also, these were students from Palo Alto, which is a pretty rich neighborhood. Right? And here's something, and here's one of the dimensions to this that I think it's not been studied very well, but I think it is relevant, right? So if we're thinking about learning how to program with trial and error, right? This is something that requires certain degrees of freedom, right? You got to have the time to do this. You got to know it's all going to be all right in the end. The computer is not going to explode, so you need a certain sense of sort of safety and security, which you mostly have if your family has a lot of money, right? And so, in particular, so this was, here's another paper. Here is the quote, right? In particular, 5% of the population will jump into it naturally, while the 80% or so who can learn it in time do not find it natural, right? So with the One Laptop Per Child project, so you can see here one of the promotional photos from that era. There's a great book, very great book, also maybe with a top 10 called The Charisma Machine by Morgan Ames. And one of the things that they found out later as a sort of post-mortem analysis of One Laptop Per Child was that there was just no cohesive strategy that would explain how poor children in Africa should actually learn and have a beneficial learning experience from this, right? And so the sort of the diversity that was one of the goals of the project wasn't realized at all. Yeah.
I sort of still have the same question.
Yeah.
Does everyone need to learn programming? Is that the goal? Is that a good goal? Well, is it okay if most people say, oh, no, programming is not for me. I'm going to leave that to the few people who actually enjoy it and want to learn it.
I think that's, I think I'm mostly talking, so in the context of this talk, I'm mostly going to talk about people who want to learn how to program. So people who enroll at a university computer science degree. This one talked about people who came into, I mean, your point is very well taken. OLPC, I think, didn't care, and it wasn't about teaching programming specifically, right? It was about any, but I think OLPC did not succeed on any sort of axis of education. That's the problem, right? If everybody should learn how to program is a great question for the panel of this afternoon, I think. So, in my personal opinion, I'm not going to talk about that much. I think the answer is yes. But it's not going to figure so much into this talk, I think. Yeah, there.
But maybe we can dampen this a bit. And instead of saying, oh, but okay, those people don't need to learn to program, maybe we can instead say, why not have a two-tier approach? Like, why not say, okay, the hackers, the born hackers, we are going to use constructionism. We're going to let them figure out things themselves. So just because it only works for 5%, that doesn't mean that it's a bad approach. It just means you have to select, you have to have something that very quickly sorts people, and then you can concentrate on that 5% using that methodology. And then for the muggles, you can use the instructionist approach, etc.
So how do you know which ones are the 5%?
I don't know. I mean,
I don't know either.
How did they know? But how did they know, right? Like they taught some introductory course, and the results of that showed, okay, we have 5%. And you know, you're not aiming for 5%. You're aiming for whatever result you deem acceptable. It's gonna be 5%, apparently.
Sure. So my goal. Okay, good point. I mean, you asked me about goals before. So my goal is, so the premise is people who want to program. And ultimately, my goal is to enable all of them to learn how to program, all of them, not just the top 5%.
No, but
right?
you can apply instructionist teaching to the 80%.
Yeah, but I want to point out that, I mean, the Purple Book, I think, is only tangentially related. I mean, it is related in some ways, right? If you look at the personnel involved to constructionism, but it's not explicitly constructionist. But it still requires you to kind of learn by futzing around and trial and error at all. And it did not work, I mean, it did not work for the MIT students, presumably, who come mostly from more...
Did
you get my point, right?
Did it work for 5%?
Yeah, if you could tell them apart, right, great. But I don't know how to do that. So I'd rather have an approach that works for everybody than have two different approaches, and I don't really know for whom what approach works. Okay. I think you'll get back to that later anyway. And I'll try to get back to that later anyway, also, right? And when we've got a little bit more context. So anyway, so here's the quote from Ames's paper. So paper claims to support diversity, but this individualistic approach to learning, it's not clear how that would work. I've got a couple more quotes from Daniel Willingham's books. One of them is that, I think one of the fallacies that One Laptop Per Child fell into is that everybody just really loves learning, right? And therefore people would just, on their own, use the OLPC or whatever tools they have to learn. But one of the sort of results from cognitive science, I'm sure a little bit, summarized maybe too much, but fundamentally thinking is work, right? And so we're curious about things, but we don't all super enjoy hard thinking, right? Even if you think, well, but I do, right? But as a species, we don't. Right? I think I'll skip all the scratch part. Am I missing something? No. Okay, just thought I saw that. On the other hand, so the good news is that if you put in a lot of work, even if you don't like it, right, then you can actually improve, right, on your brain, your intelligence, on things like this. So one way that you might think about improving this whole situation would be, well, I just need to provide better motivation for the classroom, right? So because thinking is such hard work, maybe if we can make it fun, then my teaching is going to be better. And I'm sure you've seen that. I don't know, in Germany, it seems that every 2 or 3 years, there's a great educational initiative that says, we're going to do it with robots, or maybe next year it's going to be with AI. Right? Have you seen this, right? We're going to do robots, we're going to put robots in the classroom, and then we're going to let the students program them, and because programming robots is so much fun, they will then sort of have the required motivation, so they'll put in the hard work, and they'll learn how to program. Does that make sense, right? Unfortunately, there's a problem here in that Willingham summarizes as this: memory is the residue of thought. What he says that is sort of what you spend your sort of mental energy on is the stuff that you'll actually remember. So even though you might see the robot as a vehicle to teach programming, right, what the students mostly see is the robots. They think about the robots and not so much about programming. So maybe you can impart a little bit of programming, but probably not very much. And if you've looked at some of these initiatives, they're mostly sort of, here's a couple of holes in a C++ program, fill them in, and then maybe your robot will turn around or do something like this. So I think this is also fundamentally misguided. And I'll get some more, I'll talk a little bit more on sort of the fun aspect of the whole thing. So another problem is this, or sort of, I mean, one outcome of this is maybe a reflection on a particular approach to teaching, which is also one that the Purple Book follows, which I call teaching by, or learning by example. So a lot of books work this way. Here's a couple of great programs, right? Wonderful programs. They're super, wonderfully structured, concise. They do something interesting and so on. And here's another great program. Here's another great program. And now go write your own, right? And you'll find a lot of books are like this, essentially, right? And so I don't want to dunk on Java, but I felt it was safe to do that here. So it says, hey, well, let's do this, right? Let's build a high-low guessing app. And then it says, here's a while loop, right? And here's an example for a while loop in the context of this program. And then somehow this expects the student to then figure out, while loops are for this kind of situation, and then I can generalize that to other situations, right? And so, and I pointed out that usually, I said before that my experience in the university classroom is that you get kind of these two groups of students, those that teach themselves, and those that fail, right? The ones that fail are on the left, but there's another problem. The ones that teach themselves, have you looked at their code, right? And it tends to look like that over on the right-hand side. Maybe that's not your mileage, but I've done about 1,000 students, so I feel I'm qualified to comment a little bit on that. So to summarize, so here's a couple of common mistakes, right? I think it's just very natural to assume that the students are like we are. What I love must be great for teaching. Students will figure it out by themselves. Excitement, making something exciting is going to translate magically into competency later. And also that if we can just motivate people and make things exciting and interesting, that will somehow result in an equitable learning experience, right? And so I'm really interested in that equitable experience, right? If you aren't, and there are certain reasons, there's certainly contexts where the equity isn't that much in the foreground, then you might do something else. But I'm really interested in teaching as many people as possible, right? So if all those nice approaches, and if the Purple Book doesn't work, it's time to kill your darlings. So you've got to think about some of the things that you think are very important to your teaching, and get rid of them and try something else, right? So here I'm going to talk about, I'm interested in enabling people to build houses like this or to build code like this. So I've said something on that before, so I'll skip over that. So we can step back a little bit and ask ourselves, well, how does anybody get good at something like programming or any sufficiently complex activity? And there's this famous term called deliberate practice. I think practice is actually coined in the context of golf. I think this golfer, Ben Hogan, if you're into golf, maybe you know who this is, sort of had this idea that he would really stand there and he would he wouldn't just do a lot of swings, but he would look at, oh, the swing is, the ball falls short, therefore I need to swing harder. So he would try to analyze what he was doing in practice and how good that was at succeeding in order to improve what he was doing. So it's not just enough, it's not enough to just do a lot of repetitions of something. You have to do that with the explicit intent at doing something else, that's doing something better. Otherwise, it might not work as well as you think it should. So that's pretty much, that's very well established, I think. A couple of asterisks that one put on there, but we'll go with that. Here's something else. This is a picture of my English teacher when I was an exchange student in the US in 1987, right? And it was, the strange thing happened is at the beginning of the class, she gave out this handout, and she said, well, during this class, you are going to write, a couple of papers, a couple of compositions. And then it said, this handout started with how to organize a composition. I'm going to zoom in a little bit. It was a long time ago, right? And if you look, then you can see that it had like a complete sort of structural outline of what a composition would look like. So, second part of the composition would be a body. The body would consist of usually 3 paragraphs. Each paragraph would look like this, and so on. If you look closely, there's kind of a very strong suggestion there that basically says, how many sentences are going to be in your composition and what function, what role will each sentence play? Now, you can think about what would you yourself have felt or thought if somebody had given you that thing. You're self-taught people, right? Right? And I was coming from Germany for cultural reasons. This was like, I don't need no stinking outline. I know how to write compositions, right? So I was like an instant rebel, and it took me a while to adjust. But after a while, I realized, it's actually difficult to fit a composition into this, but it's a pretty good outline, and it helps me structure my thoughts, and it helps me to get from a blank page to sort of a coherent paper, right? And, doing this over and over again, after I'd done it a couple times, I also knew, when suddenly she loosened the reins a little bit and we were given more freedom into how to write compositions, I had an idea of how I wanted to use that effectively. But my instant reaction was, I really hated this, right? So that is one thing that I sort of remembered from my childhood that kind of worked. And my compositions, I was 16, 17 at the time, really improved. Maybe one final thing on this individual, sorry. Oh, I'm already.
About giving such a structure.
Yeah.
But doesn't it make a lot of difference at which point of the learning experience you give that kind of structure? If you start teaching, somebody has never written anything before, and you give them a structure, then it'll be like a dogma. They'll basically think, I have to do it like that all the time, and that might in the long run actually hinder the learning or the innovation because they don't know how to vary the structure later. But when you give it at the time when they have already tried a few things and they've sort of run out of their creative energy and they don't know how to structure it, or they don't exceed past a certain level because they don't know how to do the bigger structure, then this is helpful.
It could very well be. It's not been my experience. I want to make another point, though. When I talk to official experts in didactics, they often say something similar to me, right? They say, well, this is bad. This is bad because really one of the fundamentals of a learning experience is that you get to look at different approaches or try different things out and compare them, and then infer things about programming from that. The problem with, I don't know how specific that is to programming, but my experience with teaching programming is if you don't give that structure at the beginning, is that a lot of the students will not manage to write their first program, much less the 2 or 3 other programs that they could compare with that one. I don't know how that goes with sort of the official position of the didactics people, but it's been very consistent. And certainly one of the things that doesn't help learning is to have a frustrating experience in the beginning. Yeah. Microphone is coming. Then make a small remark. That's okay.
No,
I'm here for the big remarks.
to turn internal.
Yeah.
I think it's a case of being liberated by constraints with this, so I can see how it can work, right? Like you have these things that are stable, and then you have the freedom, even though it's small, but you can still, you're not paralyzed by all the possibilities.
I mean, I can definitely see the argument, right, that might happen, and you certainly have to put some care in to avoid that from happening. But it's, as I said, it's not been my experience. But I don't really have for a lot of things I'm going to say is I don't have a coherent explanation. That's one of them.
Yeah, I think an important concept here would be the problem-solution ordering. So the idea is that people tend to learn things better when you present the solution after they have experienced the problem. And I think in this case, what's bad about this is that you might present the structure which solves a problem, the problem of structuring your thoughts. Yeah. If you present that at a phase where the student hasn't actually experienced that problem yet, so they haven't really tried writing an essay, or they're just not in a position to realize that they need better structure. Yeah. Then you get this response of, what is this? Why do I need this? Why are you making me use this? Yeah. Whereas if you present this at a stage where there is some realization of the need for structure, you get a completely different response, which is, hey, this could be useful. Let me just try this. And you try it and it works and it sticks and you get a nice learning experience. And I've experienced that myself in school, for example, in English class, when we would get similar advice, not this detailed, but when teachers would give us outlines. And at that point, I had already done a lot of schoolwork in this free-form writing style. And they handed us these structures. And I was like, I could use this. This looks useful. So the response you just described of rejection, I think is one that you will most often get when you're not ready for this information, or when you haven't experienced the problem.
Yeah, I think I agree with you. I'm going to put an excuse here, which says mostly that, especially at the university level, I've mostly worked under pretty stringent time constraints. So what you're describing is an approach that works pretty well if you've got a lot of time. Yeah. I didn't.
Yeah. I think as self-taught,
and you can
self-taught learners.
So now I'll try to get to the point where I'm still trying to make things work, despite the time pressure.
Yeah. Okay.
Yeah. Sorry, there was somebody there. Yeah. And then we'll get to you.
I mean, I was thinking something similar to what has been already mentioned. It's interesting that we might distinguish different phases in teaching and learning, like having a real experience of what you are going to do. So having some guidelines helps the student to have a practical experience. It's really,
yeah. No, I agree.
You collect experiences. Teaching is, I think that teaching the real powerful things of teaching is just how to abstract stuff from all the experience that I collect. Okay. And in this way, I can reuse and follow different rules, break everything, then I can create something. No? So I think experiencing actively, this is what an example like this is.
Possible. I'm going to say that regardless, even though we didn't do what you suggested here, or my English teacher didn't do what you suggested, right? It worked, right? It didn't just work for me.
There's certainly value in creating environments, where it's easier for the student to just do the actual thing you want them to do, because they don't have to worry about all the other things around it.
I agree.
I can
so
see
if you've got the time and space to do that, by all means.
Yeah,
right?
Well, it can be a shortcut where, for example, if you want someone to learn how to write a Haskell program, you can start and saying, okay, this is just the skeleton I'll need you to use, and don't worry about the import here, and don't worry about the type signature for the main function. Just focus on the body of the main function. The rest we'll get to later. But this is a good starting point. You can focus on some essentials first. So the structure kind of removes a lot of concerns.
Okay, yeah. Yeah, I think I'll return to those points also later, but yeah, so that, and that will hopefully also figure in there. We're now getting, I'm just gonna turn off my slides now. The whole thing's writing itself.
Yeah, I think one of the problems with introducing certain structures later is that they're much easier to pick up if you do them from the beginning than if you kind of self-taught some different way to yourself first and then try to get into the structure. Like I myself experienced that with test-driven development, where I think quite well understand what it's good for and I would want to do it, but because I didn't do it from the beginning, it's very hard to get into it. And I think certain things that are worthwhile doing, if you learn to do them from the beginning, it might be much easier to be actually able to do them because you didn't learn something else first.
Okay.
So my question is, so you're basically advocating for this approach, if I understand.
I'm sorry?
You're advocating for this approach.
Yes, I will.
And so my question is it a good approach to learn to write, in this example, to learn to write papers, or is it a good approach to learn to write papers that have this same exact structure? Are you getting good at actually writing papers if you start from this, or is it only this specific form of papers?
So you can have more than one outline, is what I should say, right? Right? I mean, this has happened to fit the papers that she wanted us to write for a couple months anyway at the time, but certainly the papers that followed had different structural demands. I don't know if that answers your question.
I don't know either.
Sounded more like a comment than a question.
But you see what I'm asking, right? Like because there's a big difference in my mind about teaching someone enough to be able to follow these structures and teaching someone to be able to come up with their own structures, to be able to come up with new structures that no one has ever taught.
Good point, but so I'm going to suggest that you should teach some concrete structures first, and then hopefully, I mean, you certainly loosen the constraints as time goes by, and you hope to get to the point where they can create their own structure. Yeah. So I'm sorry. Now, finally.
Okay. What do you think about teaching sort of a procedure for getting unstuck? Because sometimes I have to teach something like shell or something that's like not a functional language that is very clunky. Yeah. But I then try to give people like an intro. You can do this, you can do this, you can do this. I know this is not perfectly compositional or anything. And then I give them like, these 3 steps you shall follow if you get stuck. And like, this is more of a sort of the dual to this constructive approach. Because you said earlier that students get stuck, get frustrated, and quit or fail their exam or whatever the case may be. Mm-hmm. And the same thing earlier, Phil Wadler said, yeah, you just need a type system, and then it will help you. So how would you get a good sort of debug procedure to get people unstuck? Maybe I always specialize this to like the specific. Is it Shell? Is it Haskell? Is it?
That definitely sounds like a good idea. I'm mostly going to talk about program construction, not so much about debugging and getting unstuck. But that's also because what I'm going to suggest one other thing is that, I mean, you noticed this at the beginning, right? That I'm not agnostic. So even though you might be very interested in teaching Haskell, that eventually your students will come out great Haskell programmers, that might not be the best starting point, right? The same definitely goes for shell scripts.
Yeah, this was not my choice.
Right, if that makes any sense. So, so anything, I think, but I think generally this idea that as you observe problems that students are having, right? And the first problem is the blank page. And you can come up with explicit instructions on how to solve that problem. That is a good thing. And that is different from the example-based approach. I'm going to suggest that is different from the example-based approach that we saw earlier. I'm just going to show you 3 examples, and I'm going to leave you. I'm not going to explain what principles I used to create that code. That makes any sense. So I think I'm agreeing with you. But of course, I haven't said the things that you've said now yet. So we'll maybe get there. Okay, so far? Okay, good. Maybe here's one more thing that I'm going to throw in. You notice that the constructionist approach was geared towards individualistic learning, and I think that's sort of in the popular discussion of sort of learning. Some people say, well, great, you know, now whatever, with AI or with whatever it is, we can create individualistic learning experiences because there's different learning types and people learn at different paces and so on. And that happens less than you might think. I think if you actually look at the research, is that people are, so Willingham summarizes and says they're more alike than different in terms of learning. And strangely enough, maybe sadly enough, that is a case for that, that actually, you know, the good old lecture, you know, where somebody stands in front and tells the same thing to a whole bunch of students has a place, even in a modern educational, you know, curriculum way of doing things, right? So, so here are two things you can look at for sort of alternative approaches. One is sort of the original How to Design Programs. Has anybody read that book or looked at it? Okay, a couple people. So remember that a lot of people love the purple book. Do you love this book? You love it? What is wrong with you?
Different style, right? I
Right.
think if it was the first book, I would have liked it.
Yeah. Yeah. But you liked it? Okay, but as a teacher?
Yeah.
Ah, okay, as a teacher you might like it. Did you like it, Greg? Okay, but it's unbelievably pedantic, no? It is like, whoa, this is like some German bureaucrat wrote this probably, and well, that's what happened. So we'll get to what is it. And so it was. So this whole thing came out of a program by design curriculum by the PLT group, headed by Matthias Felleisen. And you know, speaking about the shell scripts and whatever, so Matthias also started with the purple book, observed that it did not work, and then he tried to figure out what it was that didn't work and change it, right? And one of the things, so what he figured out, well, is sort of three things that might help you teach. And one of them is called design recipes, and this is explicit strategies or explicit instructions for solving certain kinds of problems. So the important part is the explicit part about this, and we'll get to that, right? The second part is he discovered, well, Scheme, even though it seems like a great language for teaching, it isn't, right? It's not very far away from it's not that far away from a good language for teaching, but a good language for teaching is not Scheme. And so he evolved Scheme to a language that was better, or his group evolved Scheme to a language that was better for teaching. And of course, I don't know what the MIT people were using. They were probably using the built-in editor and MIT Scheme, which is like Emacs, which we all love. Oh no, Vim. But there maybe we kind of go, well, maybe Emacs or Vim isn't the best tool for beginners, right? For various reasons. I think we can, or do I have to argue that, right? And so we figured, if we want to support learners, right, those are three things that you should do. So you should think about an explicit pedagogy that we'll get to. You should also think about, do I really need to do this exact language, or shouldn't I have specific teaching languages? And also, should I maybe create a special environment that works for teaching, right? And so what came out of this was something back in the day called Dr. Scheme. It's now called DrRacket, that I'm sure you've seen. This is a screenshot, and if you want, I'll demo some stuff. Unfortunately, some German snuck itself into some of the screenshots here. But maybe what you can see, it's a very simple, there's not a lot going on in that IDE, right? There's two windows, there's only a handful of buttons that you need in your programming experience. And that's one of the things that there's just less going on to help your experience. I'll demo it if you like a little bit later. So that was one thing that they built, is a specific learning environment for programming. Then they thought about teaching languages. So one of the things that happened was that they didn't just design one teaching language, but they designed a progression of teaching languages that acquired more and more features as you went along in the course. So one thing that you can try as you're teaching Haskell or Java or any other language is, and if you look at the error message that beginners will experience, you will often see that the error message mention aspects of the language that you have not taught yet. Right? And that is the problem. That's why certain people, who's I'm not going to name, tell people to ignore the error messages because they might just scare them, scare folks, right? And this is an intrinsic problem if you have, Haskell wasn't designed for teaching. It really wasn't, right? And Java also was not designed for teaching, and that is one of the problems, right? You do one misplaced, curly braces, pair of curly braces somewhere in your Java program, and suddenly you are in another area of the language that maybe you haven't taught, and you'll see error messages referring to it, and then it's really difficult to fix a problem. And anyway, so with both Matthias's group and we have done over the years, so we designed a set of teaching languages very similar to Matthias's, but we started a little bit later, and we iterated over many years, and we're still iterating and trying to find ways to make them better for teaching. And this kind of effort has just not been done in the context of pretty much any other language. So one of the concrete things I'm going to suggest is you should benefit from that and just do this. Right? So there's an educational version of Haskell called Helium, right, that kind of made very similar observations, and it's great, and maybe you should use it for starting to teach Haskell, but nowhere near as much effort has gone into that than in the teaching languages that come with Racket or DrRacket these days. Okay? The pedagogy is based on systematic design, and we've already seen an inkling of that, maybe the outline for the composition, the 3 steps that you saw. So what we would do as educators, and certainly as Matthias would do, whenever we would teach, we would write a program in class, right? We would ask, can we explain how we did this? In such a way that the students will then go, okay, I understand these principles, and I could do the same thing. So it's based on an explicit methodology called design recipes. It's very much sort of, you have to jump through a bunch of hoops, and it's very pedantic, which is why I find how to design programs. So maybe as an educator, as a student, I think you're not going to love that book, right? And also, that has also been iteratively improved over many years, and there's many publications that go to it. One thing is, it does not try to get people excited, like basically at all, right? It doesn't go like, oh, here's this great thing, you should be excited about it. It's more like, it's a bureaucratic system, right? And so if you're doing something wrong, so probably you don't love this book. So that's the basic message I'm going to say. That I'm going to try to get across today is stick to stuff that really people have worked on for a long time, and try to find things that work by iterative improvement, and kill a lot of your darlings, right? So what are design recipes? So design recipes are explicit name techniques. As I said, they're very bureaucratic. Let me show you a design recipe, unfortunately also from the German. So for example, so one important part of the design recipe, so the design recipe is focused around data. And there, hopefully, you even and I, the Haskell people, and maybe me, the Racket person, can become friends, right? In a way, this approach is very much type-driven. You might call it type-driven. So the idea is that we look at the things in our problem statement, and we write down a description of those things in a sort of stylized manner. So for example, you could say, this thing that I have, it consists of this, and that, and that, and that. Right? If you find yourself using that kind of wording, that gives you a strong hint as to what code you should write to reflect that. In this case, when I'm going like, it consists of this and that and that and that, do a record, do compound data, right? As you might have guessed. And so we teach people to write down a description of their data in a stylized manner and then translate that very directly into a piece of code, right? That's, of course, something that you can do in any language, but we designed the language to also match the structure, the programming language to match the structure of that wording that you used in the data analysis, right? This idea that you would start with sort of the data is very old, based on something called Jackson structured programming, created by Michael Jackson. So, different Michael Jackson, but at least some people are old enough. These days, like I give this talk to Gen Zs, and I go like, Michael Jackson, they go like, anyway. So then what you do is, so you do that, right? You describe the data. That is very much You talk to the object-oriented people, that has completely gone out of fashion with the object-oriented people. That's a different story. Then what you can do is if you then have figured out if you can then sort of think of your problem as a problem that can be solved by a function, as in a couple of things go in, a couple of things come out of that function. If you can figure that out, then you can use the structure of the data to basically generate or to very mechanically allow you to create some elements of the program. So for example, in this case, so what results is what's called a template. So for example, if you're writing a function that takes a list as an input, right? You can see that in the signature up there, which is very similar to a type signature. You can see that, then you know that you can already create an outline for the function that has a lot of things sort of pre-filled in. And you can see where the 3 dots are. That's a German bureaucrat's form that just needs to be filled out. And as it turns out, so if you think about it, there's a whole lot of aspects to sort of line-to-line programming that you can systematize in this way. And if you really do that and try to think it through and use that as part of your teaching, then there's actually usually, there's just a few little gaps, right, that really are about the problem that you're trying to solve. And by the time that you've gotten there, students often find it pretty easy to fill in the remaining gaps, right? And so you make sure that they follow the design recipes step by step by step by step. And they might not like it, but by the time that they get to the end, they'll often find out that it's very easy to do the final thing that actually solves the problem that they're trying to solve. So, yeah, so that's the basic idea. It's very bureaucratic, right? We do, in the university classroom settings, we do a lot of work to sort of enforce that. So for example, we give like credit only if you do things in that sequence. On the other hand, you already get credit even if you haven't finished solving the problem, right? If you've just put in elements of the design recipes. And that is, I'm going to say, incredibly effective in getting people to program on their own. Despite the bureaucracy, despite the fact that you've given the structure sort of before you've motivated it properly. I think Matthias, when he teaches and when he has the time, he lets people fail a lot before he does that. So that's certainly composes with that approach. But it also, it even works when you're just starting like this, when you're immediately starting with a bureaucratic structure, has been my very consistent experience over the years. So let me contrast this with constructionism, right? It's so really constructionism is individualistic, but program by design is really something that works across a large sort of cross-section of your population that wants to learn how to program. Constructionism provides the tools and materials. We have these design recipes that we enforce, and program by design really does very little in the way of motivating examples, right? Instead, so for example, the high school version of this is integrated in algebra classes. So, I mean, what could be more boring than that? Oh, no, I'm at a Haskell event. Okay. Anyway, I mean, I kind of lied a little bit because there's a little combinator library for images that you can start with very early in the teaching languages, and that is powerful enough to write simple video games that we, in my university days, we would do that about halfway through the semester course. And then certainly you have to go beyond a little bit. I'm just going to, my whole experience is going to consist of implementing that design recipe and filling in the template. And people are generally pretty successful at this. So the high school version of this is the Bootstrap program. I think that's really been deployed at scale. So it works from grade 6 on, even for children. And it's been evaluated pretty thoroughly. So that's sort of the beginner's experience that I'll have talked about. So as I said, that works sort of in high school, 5th grade and up. It works for beginners in programming. It works for professional programmers as well, and I'll talk a little bit about that. Here's a strange thing, and I think, one thing that you might expect. We talked about, you mentioned a lot, what about the people who do naturally thrive by trying things out and tinkering, all those people here in the room. And when we started really getting serious on this, so there was a point in time during the lecture where we said we were really going to be serious about this approach, and we're really going to enforce it, and we're going to impose it on everybody, even the super crack students that are in this room. right? We fully expected them to hate it, right? To really feel like, right? The way that I hated the, composition outline, right? And to our surprise, that didn't happen at all, right? When the teaching evaluation came out, it had been pretty positive before. It was exactly as positive after. I can tell you one side effect, though, is the whining about the programming language completely stopped. I don't know why, right? Well, of course, I mean, you can imagine that when we came with these funny, self-designed programming languages, that people would whine that it's not Java, right? I'm sure you've heard that, right? In your work environment, why is this not? Why is not everybody doing this? Why is it not the thing that's everybody doing? That completely stopped. Yeah.
These templates for functional programming, this was like the template of simple induction function, right?
Yeah.
Are these general enough? What if you find a problem that is that you cannot solve with this template? Are there programs like this? I feel like there is a moment that when you're learning this, that your brain has to kind of click and generalize and say, that's how I can get out of the template and do whatever I want to do. But do you find this, or is the template always enough?
I think if I understood you correctly, I think both of what you said is true, right? I mean, you both realize, it both clicks, right? And then it still makes sense to you to still follow the template for what you're trying to do. It has some limits, right? Of course, it has some limits, right? But those are kinds of, so I have no idea how to teach imperative programming using this. And I know Matthias doesn't have it either. We thought we did for a while, or we could make it work, but we couldn't. So we took it out of our books, right, both of us. You can go to a certain extent, I mean, as you saw, right, this was a structurally recursive function. But this function, right, it's structurally recursive, it follows the structure of a list, right? So it's different from the iterative functions that you would ask the Java programmers to write in a while loop, or where you would say, well, you should write this tail recursively so your stack doesn't blow up or something like this. And we also, I mean, there's some amount on you can suggest some heuristics for constructing these functions, but iterative functions are, I think, objectively much harder to write, and it's more difficult to systematize doing this, right? And so that's two of the limitations of this approach, right? I mean, I still, the students that we had were still moderately successful in the second semester to write imperative programs, but I can't really claim credit for that, in that I've taught them explicitly about this. Yeah.
So this is a fold, right? Like, this is a fold, if I'm reading this right.
This is a 4?
It's a fold, right? It's a fold.
It's a fold, yeah. It's a fold, yeah.
But instead of saying, okay, you have fold as a higher order function, you instead give a template.
Yeah.
Why is that? Like, what is the benefit of a template versus a combinator?
So this will lead, I mean, once you've done this, I mean, how does a fold come into being, right? You write your data type, you write your data definition, then you think about how does a function need to be structured that processes it, and then you abstract over all of those functions. And that's what we do in class. So eventually we'll get to, after we've seen a bunch of those and everybody's super annoyed at having to type all this stuff over and over and over again, we go, so one aspect of the design recipes that is very explicit is systematic abstraction also, which I haven't gone into, right? And so you then go and take, basically any two functions that you've written in this style and go, well, now you abstract over them, and lo and behold, you get a fold.
Okay,
right?
So this is kind of like a motivation for the abstraction later. Okay.
Yeah, I mean, I kind of, I'm a little bit of two minds, because what usually happens in class, everybody gets like super overexcited about folds, right? And it's not always the best idea to write your recursive function as a fold, I would say, even when you could. But yeah, well, you're okay. Well, we can have a cage fight afterwards. But there.
I remember we had like an algebraic data type for arithmetic expressions or something. Then we had like some exercises where we wrote like the fold for that data type and had them do something with it. Yeah. And then some other follow-up exercise was like, oh, you should like
differentiate this expression. And I remember like one specific submission where somebody tried to do it with a full, but of course you can't because it's like a paramorphism. You need access to the original argument. So yeah, I don't know. I guess like in such an instance, maybe it would have helped to be more explicit and tell people like, hey, actually you can't maybe express every program like this. Well, of course you could encode the paramorphism, but then that requires more thinking. But like essentially like if you introduce a pattern, I guess maybe you have to warn people like, hey, you might not be able to express everything with this pattern.
Absolutely. Yeah, it's still, you know, the theoretical computer science people would say, Mike, you know, some things are undecidable. How could you even attempt this approach? But yeah, but I mean, I think the most important role this really plays, right? And I can only sort of tell you about this anecdotally, is to really inspire confidence. Yes, I can write things on my own. I can do complicated things or complex things. I can solve complex problems where I don't look at it and immediately see the solution. I can do this, right? You know, everything else, I think, is, yeah, I mean, as we've pointed out, right, your degrees of freedom increase. Maybe you can even self-teach a few things to yourself. But I've you know, observing students, I've always found it always seemed to me it was just devastating to them that if they couldn't succeed early in a class, right? And this is also a cultural thing. So in Germany, I would often observe that the reaction to this was, oh, okay, I'm obviously not cut out for this kind of activity, you know, but I'm stuck in this degree program, so I'm just going to copy somebody else's homework. You can translate this to today's AI situation, I think, without any changes, right? So I think that's the most important rule. So if you later, so I don't think it's a problem that this approach, of course, has some limitations. I don't think that's the biggest problem that you have here, right? Does that make any sense? Right? Yeah.
Yeah, so when you said focus on excitement, I think it actually it actually kind of does, but it doesn't try to create artificial excitement through robots or whatever, but it guides students towards being able to do the thing themselves and get excitement from that.
That is my sort of armchair explanation as well, right? Yeah. That hasn't been empirically studied, but I mean, when I talk to the didactics people, right, they tell, you know, intrinsic motivation, and I think they're right? But then they say, well, you should explain to students why you're doing things, right? And I'm sure you've done that, right? You've explained to people why functional programming is the better way to go, and you've not always been successful.
Rather than explain.
It's because you're explaining it in a situation where really, you know, your conversation partner can't really understand what you're saying. It's one of the fundamental problems, right?
I think demonstrating it is usually more fruitful than trying to explain it.
So now you have this conundrum, right, where you want to demonstrate, of course, that what you're doing is good, at least. It doesn't have to be superior to everything else, but that it works, right? And therefore, in order to get there, though, you have to get people to do things that work. And in order to get people to do things that work, they're better off following the design recipes than doing it on your own. So just to get into a little bit more of anecdotal detail, so one of the things we would do is also to get more data on what students were doing, was working, we did part of the homework, we would do that in a supervised setting. So we would look over students' shoulders while they were doing it, right? And a very typical situation that occurred over and over again is in the first like 2 or 3 weeks, right? We would look over somebody's shoulder and they're supposed to write a function that is going to end up being 4 lines, and they're like on their second screen already. And they're finding out it works for like 3 inputs, but the 4th one, you know, it's a special case, so I'm going to add more code. I'm sure you've seen that, right? And you can go, you know, and I learned how to do this, right? I would go and say, well, you know, shouldn't you try to do it the way that we've taught you, right? And they would go, no, I would rather do it on my own, right? And I've learned to then, instead of saying, well, but here's how this approach is, let me explain it to you, I would just go, well, you do have 20 minutes, right? And they would go, this is being recorded, right? There we go. Right? So they'd be really angry at us, I feel, in the first 2 weeks. But then I think some people, I mean, there were some incidents really almost, right? Where people were shocked to realize that what we taught them worked, right? Maybe a German problem, right? You tend to, or maybe a German issue, right? So that's one of the things that would typically happen. So we learned, we really learned, I mean, by me, I mean the whole team that we had, right? We had a large team of people who would both lecture, we had a whole bunch of tutors. I already told you that the crack students, to our surprise, really liked it. And we had zero problem, we had like less than zero problems recruiting tutors for the next year. Despite the fact that, I mean, so we really decided 1 year, okay, we're going to get serious about this. We're going to enforce the things that we just try to motivate earlier, right? And so we're not going to. So we said. So I kind of hard to imagine seeing me now, I guess. But before I'd been wearing like long hair, and I put on Mickey Mouse T-shirts so that people would feel comfortable talking to me and asking questions and so on, right? And so I cut off my hair. I put on a suit. There's still recordings of this. I did not make a single joke during the entire lecture. And students sometimes say, well, I can see your mouth is twitching right there, Mike. We would start the first lecture by, so as I say, whenever somebody would say, why are we doing this? I would just say, well, who's the expert? Is it me or is it you? Right? We would have, a detailed sheet of all the things that people do. We did things that were against the Geneva Convention, literally. With the only goal that the results on the final exam would get better, right? We fully expected people to absolutely hate it, and they didn't. Go figure, right? So I think the explanation is exactly what you said, right? Is that even though there wasn't any positive motivation in the class, they realized, oh, I can do this thing, right? But you have to get them to that point, right?
Circling back to one thing that you said, it's hard to explain to your students why they should be doing, let's say, functional programming instead of something else. I still believe that students can appreciate the difference already very early, but they need an honest comparison. Like in many German, like in the uni where I taught Haskell for some time, they first learn, I guess, Java. And then in second year they can learn Haskell if they want, but they don't need to, and it's very maths heavy and so on, and it's combined with logic and with type theory and whatnot, so many don't. But what if you tell them, okay, we are going to teach you at the same time, we're going to teach you, let's say, this Racket and maybe another programming language, say Java if you want to be really mean, and then they have to solve the same problem in both languages, and then maybe at the end they get to choose which language they prefer, and then you'll see, well, what will they choose? Have they maybe already learned that?
Sounds like a good idea. I haven't tried that. Right? Honestly, sounds like a good idea, right? I have not tried that. So, I mean, one of the problems with this is you iterate, but your iteration cycles are like a year or even longer, all right, sorry, I didn't see you back there.
So I come from a very, different perspective in that I never formally learned programming through a school or anything like that. Haskell's my first language, and work taught me C. And the only real way I could get any kind of appreciation for either language was having it available. So I kind of echo the last point, which is it's nice to be able to have at least two languages going at the same time, seeing how you'd solve the same kind of problems in either. And then, seeing if you can accommodate features from one in the other. So like one of the things I like doing in C is like modeling new types, because every time I go to C, I really wish I had them. And I found different like kind of macros for doing so. And, trying to do polymorphism in C as well. Very annoying, but it can be done. But that's when I realized how much I appreciate Haskell. At the same time, when I'm doing very direct memory stuff in Haskell, I kind of wish I had, just the same ease I had in C as well. So I think, just having like two languages at the same time that can help you appreciate what it is you're doing and solving the same problems can show you the strengths of one versus strengths of the other, and then trying to figure out what's the gap that you can bridge in either language.
Yeah, that sounds great. Yeah, I mean, let me be clear. You know, what I'll tell you about the things that have worked for me, right? That doesn't mean it's the only way that things can work, right? And so that sounds definitely like something to try. Yeah. Okay, so far? All right. Before we get into more anecdotes, where were we? So I've been thinking about equitable programming. Okay, so if it's okay, I'm going to switch gears a little bit. So this was sort of about the introductory experience. And what happened in my career then is that I had more to do with teaching professional programmers, right? And so most of sort of the stuff that we gathered before was from teaching the intro course. And then as part of my professional activities, sometimes people would come and ask us to teach a course on a specific functional programming language. And more recently, we've been teaching classes on functional software architecture, right? You've been in there, where we actually also use Haskell. So I'm going to talk about that one a little bit. I don't know if I have like exactly the right slides, but we'll find out. So this really is not just about sort of writing small programs, but what happens when our programs get larger or when they get more realistic. We can think about, so there's a lot of people that have thought about software architecture more in the context of object-oriented programming. But this is, I think, one of the shortcomings, one of the failures, I think, of our community is that we've done very little to communicate and think about, well, how do we build large-scale software, right? And so so when we started teaching this, I kind of realized that, well, it works good it works well for marketing purposes, but I don't really know what I'm talking about. So when I think about functional software architecture, I mean, of course, I've built, and a lot of people in this room have built substantial software using functional programming, but what are the principles that we've used to do this, right? And how does that fit into the overall landscape of sort of software architecture techniques and things like that, right? And so I'm going to make a few suggestions that have worked well for us, both from a didactic standpoint. I think they also kind of are good from a pure software architecture perspective. So first of all, I think we're used to expressing things as pure functions, right? And the one way to think about it in terms of software architecture is the business logic, right? Whatever happens in your domain, that you would write this as pure functions. That is worth saying. Another thing that's worth saying is that your interaction with the outside world is something that happens at the edges of a system, and you don't have that all over as you would do in sort of classic, Java-style software architecture. We design data types that capture domain logic, which is something that now, hopefully, we can see how that goes back to the introductory course. We talk about things like parsing, parse, don't validate. That's definitely something that is that is very different from the way that the object-oriented folks approach things, that we're declarative, and that we have laws and properties of data at the design stage. And somewhere there's missing, let me add that, it is a bottom-up. I think we mostly do our software architecture bottom-up, which is worth saying because a lot of people these days do software architecture from a top-down approach, right? So it's sometimes kind of difficult to the software architecture people because there's many definitions of that term. I really am interested, when I say software architecture, I'm really interested in software that lives for a long time and hence grows large. So all the activities and all the things that you need to think about when you have large pieces of software that are different from just having to write your typical, textbook 4 lines of Haskell. That is software architecture. And specifically, when it gets really interesting is that when you have multiple, when there's not just one person writing the software, but when you have multiple people or even multiple teams. And I should note that software really we're building that to fulfill requirements, and preferably requirements by humans. right? That sometimes gets, strangely enough, gets kind of forgotten specifically in the sort of functional world. One of the things that requires communication when you talk to software architects is that a lot of software architects approach software with a sort of stance that says functionality is really not important, right? There's all these other things that are important about, I mean, this is a popular book out of Carnegie Mellon on software architecture. It says functionality does not determine architecture, right? Functionality is trivial, right? Is that your experience? Functionality is trivial? So it's not mine either, but a lot of the software written from those books, functionality is kind of trivial, right? Yeah. Yeah.
And which one is the best doesn't depend only on the functionality.
No, it depends on a lot of other factors as well, but it certainly also depends on functionality. Wouldn't you agree?
Of course, yeah.
Right. Yeah, you say of course, but see that, right? So one of the things that the software architecture people think about is they think about all kinds of other properties, so-called qualities of software. So there's this is the ISO 25010 standard, I think the slightly older version, which defines sort of vague categories of properties of software. And my friend Markus Harrer did a survey among software projects as to when those different aspects of software project come into focus, right? And not very surprisingly, what's called functional suitability in ISO 25010 is first, and then you have all these other qualities that come into focus later. And you see the problem there from the sort of traditional software architecture standpoint is you have to account for all of those other qualities, but they come into focus after you've started. Does that make sense? Right? And so, and specifically, you know, sort of, I think the sort of magic or the most important quality, I think from a software architecture standpoint is the one there, it's called maintainability that you see there, right? And why is that? It's because as software projects go, the money doesn't go to the initial development, it goes to changing the software later. Right, that's where the budget goes. So if we can make that cheaper or more efficient, that's good. Unfortunately, it often comes into focus late in the project, which is why if you've ever done software reviews, a lot of software projects don't look very good, right, if you do this. So maintainability very late in the game. I'll point out that, you know, sort of the software architecture community has produced a lot of literature and a lot of sort of approaches and techniques and things to deal with that kind of situation, with doing large teams, most prominently domain-driven design. Who's heard of domain-driven design in this room? Okay, at least, most people, but not everybody. But you'll notice that all of those books are kind of books on software architecture that are outside of functional programming, right? Well, except for one, right? Well, right, that one. That one, right? It's a purple book, right? By the authors of the purple. Who's read that book in this room? Yeah, Farhad, okay. See, there's the problem, right? Actually, a pretty good book, right? It's pretty good. So because of all this, right, because of all those unknowns, we developed a curriculum for an organization called the ISAQB on functional software architecture, and it's what's called an advanced level curriculum that you take after a sort of foundational class in software architecture. And the foundational class covers things like requirements and design techniques and specification and communication and analysis and stuff like that. And for the curriculum on functional architecture, you can see there in the beginning, there's sort of a basics of functional programming, and then there's other aspects, functional modeling in particular, and functional macro architecture that follow. As you can, and the way that we teach it is we do, how many minutes you're supposed to spend on this? Yeah, good point. In class. So this is designed for a 3-day class, right? The curriculum sort of postulates a 3-day class. The way that we teach it is we do an introduction into functional programming. We do an introduction to Haskell on the second day, and then we talk about all sorts of sort of modeling aspects of programming. So I like to say, so when I talk about functional programming these days, it used to be that we're saying it's called functional programming because functions are first-class values or something like this. I think the way to talk about functional programming to sort of outsiders these days is it is about data. Everything is data in a functional program. And you might wonder, well, isn't that the case everywhere, right? Isn't it? No, right? If you look at a lot of other projects, you'll find out that the data is very secondary and that people don't spend a lot of time and care on the data. Huh? The idea is older, yeah, but mostly you find it in the functional programming community these days. Originally, of course, it's an object-oriented idea, right? So object-oriented design very explicitly was about data modeling. I know. Jackson structured programming, for example, right? That is from the 60s, at least, right? And it used, in Germany, computing used to be called EDV, electronic data processing, right? And so we've kind of lost that, I feel. Unless it's like sort of LLM data, lots of like matrix. Anyway, won't get into that. So, data everywhere. I think I deleted a few slides a little too late in the process. So, I've deleted a couple slides. So one of the things we thought about was, so we want to teach functional architecture and functional programming to professional programmers. Our experience is in teaching functional programming or programming to beginners, for people who've never programmed before. So we've got to do things differently, right? And so our thinking when we started this about in 2012 was, remember that there was these three pillars to the program by design approach. One was the pedagogy, one was the programming environment, and one was the programming language, right? And the reason for the programming environment and the programming language is that beginning students tend to get overwhelmed by the details of the language or the programming environment. Now, we were dealing with professional programmers who've seen, IntelliJ or Eclipse, which has a gazillion, menu items and panes and, panels and search functions and whatnot. And they've certainly seen, programming languages with terrible error messages in their lives. And so therefore, we could just focus on and we could just focus on the pedagogy and do whatever programming language we wanted for the actual architecture class. So for the architecture class, we wanted to use Haskell because there's a lot of things in that language that we could demonstrate. Things like concurrency and parallelism and using types to leverage in software architecture. There's a rudimentary module system, so it can serve sort of as a vehicle for demonstrating a lot of things. So when we started teaching Haskell courses and also courses for F# and OCaml and a couple of other functional languages, our thinking was we're just going to start with these languages, but we're going to use the original pedagogy that had worked so well for us, right? And it was okay, but it wasn't great, was my experience, very consistently. And so, by now you've noticed, hopefully, that the way that we felt, the way that we feel is to improve such a class is by making iterative experimental changes and see how they work out. And so we experimented instead doing a highly compressed version of the introductory class for the professional programmers, but with everything, with the teaching languages that we designed for the beginners and with the programming environment that was designed for beginners. And that seems to work much better. So interestingly, it's pretty rough actually. So when people come into the architecture class, they take 1 day of an introduction to functional programming, doing a highly compressed version of the introductory class. And then on the second day, we teach them another programming language, Haskell. And then we go from there. It's pretty rough, right? But it seems to work pretty well. And for a wide variety of, sometimes we really have software developers, sometimes some managers for some reason, right? They got lost somewhere, come into this class, and they also seem to be doing pretty okay. And maybe, I don't know who it was here, the thing is, right, people pay for this class. So I always feel that I can't really tell them, well, you've got to stick to this, otherwise you're not going to get any credit. So what I tell them usually is, well, you're going to think this is all trivial, kindergarten stuff. But on about the third day, about at 10 a.m., you will come across a problem that you can't solve by I'm going to do it on my own approach. And I think that's when they realized the value of that. So maybe there it is a little bit that way. Right? I forget who it was that mentioned that possibility. So that definitely, so I feel that that probably works as well. Right? Was it you? Yeah. So anyway, so there's that. So, and then indeed after that, we sort of go over a lot of the same material. I tried to do that yesterday at the beginner's track. It was pretty rough as well. It's also kind of cool, I think that, I mean, I haven't shown you much of those teaching languages, but they are based on Lisp syntax, so very different syntactic constructs, right? The Lisp people love parentheses, the Haskell people, who hates parentheses in this room? Right, there you go. No, the rest of you also hate parentheses. Right? No, Greg, you don't? No. Every time you type $1 instead of doing parentheses, you hate parentheses, let me tell you. So, so it's got static types. It occurred to me that I never talked about the typing aspect, so I'll need to get to that. That you really, the monadic effects, really Haskell language server is really, really good for teaching, has been my experience. Really, really good. I'm really very pleasantly surprised. We also have a Scala version of this that seems to work equally well, but the Scala code is basically very similar to the Haskell code in structure. Yeah?
Code in the IDE, you had like the Haskell code being evaluated with like the eval plugin, so like evaluation through HLS. Yeah. Do you get students using that?
Yeah, all the time.
Does that work well?
Yes.
Nice.
I mean, it's a replacement. Again, there's a lot of details I didn't go over into the teaching languages. One of the really helpful things in the teaching languages is that you can write your program elements in the spatial order that corresponds to the order and time that you do things. So in particular, we ask people, write a short description, to write a signature, not a type signature, but a signature, and then a bunch of test cases. So the test cases are before the definition of the function. And there's not really a super cool, testing framework for Haskell that let you do this, but this comes close, right? In that we would just make those eval comments right in exactly the places where the tests used to be in the teaching languages on the previous day. Yeah. So, yeah, that works. So it occurred to me, I'm sorry, I forgot that I don't really have a slide, but it was you who asked about types, right? Or somebody asked about types. You asked about types, somebody in the back, right? You asked about types. So again, right, it's about enabling people to write programs, particularly in the face of having made mistakes, right? And so what we do so the teaching languages in DrRacket, you would call them dynamically typed, even though there's something like a type signature. Maybe I should show you this. So, these my eyes have. So is that, now we can make that bigger. That big enough, right? And so if you were there for the beginner's track, you can see that we did the exact same example that we did there too, which is that, well, you kind of start with a simple data analysis. A pet is one of the following: a dog, a cat, or a snake. And you can see in line 16 here that you've got something that looks suspiciously like a type signature, right? You see that, right? So if we run this program, imagine we made a mistake, right? And we went like check expect a parrot, right? A parrot, is a parrot cute? Yeah, it's cute, whatever, right? And you would do this. So what happens then is you get what's called a signature violation, right? So this, however, got generated at runtime. So it tells you the value that violated the signature, and it will also tell you it will also tell you exactly where that happens. And so that's the problem with type error messages, is they can't really, usually they will not produce a concrete situation that will indeed run into the type violation. Instead, they will say, as Bob Harper likes to say, well, your constraints were not solvable. That's all there is to say about your type failure. So that's the fundamental thing. So the feedback that you get is much more concrete in the sense that your program actually did something that violated the type signatures there. And that, so I think, we've always done this. Matthias did a lot more sort of empirical research on, what kind of error message is better. But this kind of message has consistently come out on top. I should say that, right? But once you've done that for a little while, right, and then you switch to type error messages, that seems to go down pretty easy. Yeah.
Like once students are like maybe in day 3, day 5 or whatever, is it possible to maybe tell them that this all chains into each other? Like if you have types that don't model some technical thing, but actually your domain, then your error message actually starts at least getting a little bit better.
Yeah, absolutely.
And then all of those different approaches sort of combine into...
That's what happens. I do read the error messages with the students, right? I'm not like that dude.
And maybe in the Haskell course, like specifically for Haskell, do you teach the students something like, I don't know, debug trace or something if they have a bigger function where they want to see what's going on, or?
No, that doesn't necessarily mean it's a bad idea, just for reasons. The problem is it's an architecture class, right? And so it can't exclusively focus on sort of programming tasks, but we at some point need to get a viewpoint that's a little bit higher than just individual lines of code. And so I don't think it qualifies like as a full-blown course in Haskell programming. I think it gives you enough ideas to then hopefully make it on your own if you're interested in doing an actual project in Haskell. And people do get productive in doing things, but of course all this is in a context where there's some supervision and some group work. So it's not the same, it's not quite the same as enabling people to do every line of what is being covered in class on their own. Right? That's not the goal here. If that makes any sense. Yeah. Is there another question there? Okay. I'll tell you one downside is Haskell really is difficult to install on random machines to this point, and it seems like whatever works this month might not work the next month, right? So we keep revising our instructions on how to do it. Here's a couple other things that I've discovered over teaching this course. One of them is that, having algebraic data types, right, and having, I didn't really talk about this very elaborately before, but this data modeling approach at the heart of how to design programs is really about distinguishing sums from products, right? From saying this is this and this and this and this from this is that or that or that or that, which is of course all baked into the mechanism of algebraic data types. This distinction and thinking in terms of sums and products is something that's virtually unknown outside of functional programming. So we kind of accidentally, sort of teach that very explicitly and elaborately as part of the intro class, but it's really something that beginners and professional programmers have in common, that they don't know this, right? And the depth of the lack of knowledge in this area in data modeling is just astounding to me, right? On the other hand, once you've covered that, you can do things like, you can do, for example, Simon Peyton-Jones's and Jean-Max Libert classic paper on financial contracts. I don't know if anybody's, so go read that paper if you haven't, right? Most of that can be done as an exercise now, if you do this. I always find it funny that, this paper starts with saying, any red-blooded functional programmer is going to build a combinator library in 2001. Yet where is the book that explains how to do it, how to write combinator libraries, right? And there exists one now that I know of, right? But it was written fairly recently. Sandy McGuire's algebra-driven design is on this, right? We also write a full application on a little card game, the Hearts card game. That's always kind of where we really do this bottom up. So we start with a domain logic and then work ourselves up to sort of an application framework where there's even a front end. I should probably go over this quickly, and then you can ask detailed question if you're interested in anything, but it can serve to cover sort of a lot of aspects of architecture, the bottom-up aspect, the data modeling aspect also, because we do this driven by events, which is something that software architects also know, and so you have this idea of having a data type for events and commands, which enforces this idea of that everything is data. And you kind of have gameplay as this sort of cyclic process of events and commands that go back and forth between the game table and the command. One thing I realized, and then a while later talking to Andres, one thing really that I struggled with was how to teach doing like effects and monads and things like this. Right? I don't know if you struggled with this. And I think one of the issues we have with that is that we generally tend to teach monads in terms of sort of technical monads, right? The state monad, the exception monad, and things like that, right? And I think that is not the right way to think about it. The right way to think about this is to think about it in terms of process in your domain, right? So not in terms of technical things, but if you have a process in your domain, that you would model it with a monad. And the reason is very easy to see. If you see this program, this is a classic functional thing that tries to explain what happens when a command from a player comes in and it operates on the state of the table. Then you have the succession of states that you see here. State 1, state 2, state 3 that you thread through your program. If you do that explicitly, it's hell. Right? And it's particularly hell when you're doing it in Haskell because of the fact that lets are recursive. Okay, kind of, okay. So this is the place where you introduce a monad and where you let people invent, the things that happen in their domain that then correspond to monadic commands. And I think this is not just the right didactic way, this is the right way to write programs. Right, is not worry so much about the technical monad, the technical effects, but really use monads for domain modeling for things that are sort of sequential in your domain, right? And then just write a data type for that. Don't do MTL, and also hold off on the effects library. Effects libraries are great, but it really is a good idea to just start with a good old, so here's how that program looks monadically, all that state manipulation, that sequential state manipulation has gone away, and you really see, if you know the Hearts game, you kind of see, you recognize the way that game works in this, right? This is also an exercise that the students in that class do. And then you just write a good old data type with continuations, and again, you drive home the idea that everything is data, your processes are also data. And of course, you've kind of implicitly introduced the concept of continuations as well. Monads we do via using a simple DSL for databases, and applicative functors we do via deserializing JSON objects, right? So generally validation, you remember, parse don't validate is one of the things that you can use. And so what kind of we've come up with over the years, which are sort of sensible concepts or sensible type classes from the Haskell ecosystem to teach, are those 5 here. I think those get you the biggest, the best sort of bang for the buck is if you know those 5, and it is possible to cover all of them in a sort of 4-day training. You kind of have to watch out because we as Haskell people, we think of, well, your program is functions and data, and right, your program gets bigger, you write more functions and more data types and things like this. And if people come from outside, they look at this and they think, well, but where's the software architecture in this, right? You really have to reinforce that point that no, it's okay. Your software architecture is more, because of that bottom-up approach, is really more sort of an emerging thing. So I really need to wrap up. Does anybody know this book, the Green Book, by the way? Sorry, I'm kind of cycling around, right? So this is kind of one of the original sources for the term coupling in software architecture, right? And I mean, it's not quite empirical research, but these people, this was written in the 70s when people knew very little about sort of the pragmatics of programming and software development. And they thought, so they really looked at software projects and asked themselves, what costs money, right? And one of the things they figured out, is the money goes into changing the program after it's been initially deployed, not in the initial development. And then they asked themselves what makes programs easy or hard to change, and then they came up with this concept of coupling, right? And what is coupling? Coupling is dependency between different parts of your program, so that when you have to change one, you also have to change the others. And the way to talk about this in the context of programming, of functional programming, and then hopefully that makes some sense to you, is that if you do it systematically, functional programming is a way to write software in a way that is decoupled by default. And that is different from the experience outside of functional programming, where people have to work really, really hard to keep coupling low and have to keep refactoring, right? And so I'm sure we're not always succeeding in functional programming, but certainly I would argue that coupling in sort of large functional programs is an order of magnitude lower than in comparable projects. In the sort of non-functional world. And this goes back to this diagram here that we saw in the beginning. Therefore, it is perfectly okay, we're getting there, this diagram, it is perfectly okay to think about functionality first, right? Because all these other qualities come into focus later. You tend to achieve them by changing the program, and you maintain your ability to change the program by the functional programming. And I think that kind of goes well together, right? So functional programming means you go attend to the functional requirements first, right? It's kind of a coincidence, but I still think it's kind of nice, right? So, and that really differentiates it sort of from traditional software architecture. So, some indication of this is that if you look around, you will find the term of the modulith, the modular monolith in sort of traditional software architecture reflects the assumption that the software community at large has completely forgotten how to develop modular software unless it is as a bunch of microservices. So this is something that might seem trivial to you, but it is really very much worth saying. So anyway, functional software architecture, bottom-up architecture. One other way, I mean, when people say, where's the architecture? I say, well, our job is to avoid making like big decisions. So one way to think about it is that we're trying to avoid architecture, and we do the functional qualities first and the rest through changes, which hopefully are easy. So we've done about 30 iterations so far. Feedback has been uniformly positive. We get functional programming newbies who have done nothing whatsoever to being able to, for example, do large parts of this financial contracts thing on day 2. And being able to do stuff in the context of a larger project on day 4. So if you're in an organization where people are skeptical about their ability to learn sort of functional programming, this is the positive message of the day. All of this stuff is eminently learnable, and it's eminently learnable for everybody who's working in software development, right? And so on the other hand, we really need to talk about this stuff explicitly, right? There's very little in the way of books. Even like the obvious things like sons and products are under-communicated. People outside of functional programming know about that, don't know about this. And I'm sure a lot of things can be done better through iterative improvement, and certainly the course on functional architecture, also the introduction to functional programming. I still find little tweaks that make it better from iteration through iteration, right? So if you're interested at all, or you know people who are interested, we're teaching functional architecture a couple more times this year in Hamburg, actually in end of this month. There's also an online possibility, and later again in Hamburg. Okay, that's what I have to say. It's a long talk, but we got time for a few more questions, right?
I have a question.
Yeah.
So, in the context of a university, if you had your way in designing a program in this area of programming, given that they need to learn how to program, but also the expectation is that when they go out, they need to know Java. Maybe I would like that they know how to do functional programming. I guess the operating system people would like them to do systems program. What would you see as the right way to do this?
Okay, tall order, of course. So, I mean, I think I've talked enough about the intro class to motivate that is the right way to do it. In our university days, we often used to follow that up with an introduction to object-oriented programming using Java, for example. So we slightly modified, there's also educational programming environments for Java. One is called BlueJ that we modified a little bit. But we really made it go well structurally with the stuff that we taught before, right? So the data modeling stuff, we would carry that over to object-oriented programming. I say this explicitly because the object-oriented people don't do data modeling anymore. So this is different from your average Java class that you would do. So I think you can really do a pretty smooth transition from after all, the original goal of object-oriented programming was very much like what is functional programming today in many ways. So there's no mismatch or anything like that between those two things. And then it also becomes possible to at least mention imperative concepts, and then students seem to be able to deal with them as well. I definitely think that students benefit from some introduction to software architecture. So the aspects that I've just mentioned, right? The fact that large software architecture might require thinking about some things that you don't think about when you're doing small software pieces of software, and to really talk about what is it that makes software, hard to maintain, about doing those different qualities, about doing approaches for improving on those qualities, and then tie that back. But I find it, there I differ with my software architecture colleagues. I really think all of this should be tied back into the process of programming. So I think that is sort of the main sort of strand that I see there. I'm not sure I have a strong opinion on things like operating systems and things like that. I mean, one of the problems is I'm just very old. So all of that stuff I did a long time ago, and I probably use it when I'm programming, but I'm not sure what exact subset is it that really has the most stuff. But the central thing of that line going from programming, different kinds of programming, after that, and software architecture, I think that would be a good thing to do for universities.
Okay, thank you.
Yeah.
From the other side of the spectrum, like in business, what would you say is the minimum that makes sense? Like you said, your course takes like 4 days, I think.
Yeah.
So do you think it makes sense to introduce concept or at least vocabulary in a smaller packages, or is 4 days like the minimum that allows you to...
You're trying to do what?
Well, for example, monoids for me are very useful. And stuff like that, like or functions, like small functions are useful. Does it make sense to show these concepts in isolation, or do you like need a large, like several days to build a motivation for it and actually drive home like some understanding?
I'm pretty sure if your goal is just to motivate things, right, you can do this much shorter, right? So, but if you're thinking, I mean, what certainly has happened is a couple of people have gone through this course and then went on to work for our company a little while later. And there it seemed to be sufficient to then, go the rest of the way and do their onboarding and do most of that on their own. I feel that's pretty much the 4 days feel very fast, right? Johan is no longer there, but you could testify to that. And I don't, I'm sure there's some bits and pieces you could leave out, but that would not substantially shorten it. So if you really want people to if you're really interested in the perspective of getting people productive in a larger functional project, in your Haskell software project, whatever, right? Then I think those 4 days, you should probably not do it shorter than that.
Well, my motivation wasn't like to rewrite the world because we don't have large functional application.
But some people do.
Yeah, right? Yeah. Well, that's great for them. I would love to be there, but I just want I have a smaller goal of like introducing the thought, like, and if that's possible without
introducing
them a lot of practice.
Introducing the thought can be done in a single day, right? That is the first day of this training. I feel, I mean, the next step up when you think about what could people do in the context of their Java, what of this could make their Java project immediately better, then is the data modeling aspect of this, right? And so you would, again, that first day that I mentioned is really big on the data modeling. You would still need to translate that into a Java context and do a little bit of more practice. You could probably squeeze it into 2 days. 2.5 days, I think 3 days would be better, right? But you could do it in less than 4 days, pretty sure.
Cool, thanks.
Right? Yeah. There's...
Hi, this course was like modeled for students that are already interested in computer science or have an understanding of what computer science or programming is. Is that correct?
Those are two different things, right? They want to learn about computer science. They have an idea of what it is.
But they're technically interested in it.
So the intro course, right?
Yes, like the one that you are talking about.
I mean, those are people who chose either a major or a minor in computer science, right?
My question would be, do you think these conclusions or a new way to teach it that you found with this course also applies to people that don't like or don't know what like programming is, or is this specifically only for people that already know what they want to take away from this?
Yeah, so I don't have the experience to back this up, but you remember that Bootstrap spin-off project that I mentioned, right? And that is and the way that is, I think, usually being integrated in the curriculum as part of math, right, of the algebra class that's there. And there, it's certainly not just, so it's part of the regular algebra class that students are taking, and it's not something where people go like, I'm interested in computing, therefore I'm going to pick that class. And that, I mean, as I said, they've done a lot of evaluation that is uniformly positive. So I think the answer is yes, right? One more?
One last question.
Yeah.
This is not a question, it's a comment. So suppose that, I don't know, you have person one, he does like this, or they do this 5-day course or something, they become productive, they spend the next 20 years being a line programmer in some big organization. And then you have some other person who does, like, meanders through CS, self-driven, learning and then studying deeper concepts. They dive deep into everything, and because of that, it takes much longer for them to get to the point where they, and then they spend the next 15 years instead of 20. They only have 15 years that they spend, but not being a line programmer, but someone who's like working on interesting things. Yeah. So your title of your talk was Teaching Your Loved Ones.
Yeah.
I would like my loved ones to go the second route, because I think at the end of the day they get more pleasure from the whole process.
Okay.
Yeah, this is my remark. And then you die at the end anyway, so that doesn't. Yeah,
that might also work, right? But it might also not work, right? Is the point? I'm trying to make the point that it might not work at all, no matter how much time you put in. Right? It does not work for everybody. So I think what we're doing for the intro class pretty much works for everybody.
But you don't need equity for your loved ones, because that is individualized.
I was trying to be a little provocative there, as you might imagine. So point well taken. Okay.
Could I ask something? So how much of this is, so this is a live class with live people. So do you have experience with teaching without live? I mean, I'm not talking about AI or dead people. I'm talking about just with the book. Yeah. Yeah.
No.
No. Okay.
Really.
Okay.
Right. Yeah.
Yeah. Okay.
So, I mean, one thing that I found out is that, but that's only tangentially related, right? But it's kind of, one of the points I was trying to make earlier transposed, right? I mean, we're all trying to convince other people of the goodness of functional programming. And of course, I try to convince a lot of people of the goodness of this educational approach. which totally did not work. But since I've stopped doing this, people sometimes stumble upon that book, right? Teachers, school teachers, and so on, and try it out and seem to be successful doing that. So maybe the answer is yes.
Got it.
Yeah.
Got it. My last question. So everyone else, close your ears. You said you had experience with imperative programming as well in a systematic way, and you said it didn't really work out. Can you maybe elaborate on that a little bit?
Well, there's a chapter on imperative programming in the Purple Book, right, which is based on sort of environment diagrams. And again, it's one of those things that seems very compelling, especially if you know how things are implemented underneath. You think, yeah, this is the way to teach this. And here's the depressing story. We try to make that work over multiple years. And I felt that, okay, the problem is the environment diagrams could be drawn better. And so we put a lot of care and work into, having really good explanations. And the result just would not get better. So eventually, and here's the depressing thing, right, is I figured, so here's a tip if you're an educator, right? I figured, okay, so we're wasting 2 weeks on this subject, right? And nothing comes out. So now we can just cut all of that and we can use those 2 weeks for something else, right? You should do that now and then, right? If something doesn't work, don't try harder, right? Just throw it out, try something else. And so we figured we're just going to use 1 or 2 hours of those formally 2 weeks, and I'm going to do a bunch of hand waving at the blackboard and sort of going, yeah, well, you set the value of the variable, which is totally not what happens, and so on. And depressingly, the results not just stayed the same, they got better. Right? Okay. I don't know why that is. So, but on the other hand, the imperative programming at the end of the second semester, where we would demonstrate, admittedly, we would go from, okay, here's essentially your functional program, and we see that we're threading something through the program. We can just use a variable for that, seemed to work much better, right? So that's a limited view, of course, of dealing with state, but that seemed to go down okay.
Good. Yeah. Thank you very much, Mike. Let's thank Mike again. Yeah, I was really happy. So Mike has been here for 2 tracks. That's actually quite rare. Thank you very much, Mike, for coming. I heard this talk at ICFP 24, and I was like, yeah, we must have this at ZuriHac. There are many people interested in teaching, me included. And so it took some time, but thank you very much, Mike, for coming over. Thank you for giving us both these tracks. Thanks.
Thank you, and thank you all.